Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Department of Physics, Himachal Pradesh University. Today we are going to discuss about module Surface Physics Characterization Techniques 2 from paper Solid State Physics. So students, let us see what we are going to learn in this module. So we are going to learn X-ray reflectivity formalism and phenomena of total external reflection. Reflectivity from flat and rough surfaces, and the role of roughness in the reflectivity. Also, we will know that how to calculate the reflectivity of a thin film, analyze its analysis scheme, and what are the advantages and disadvantages of X-ray reflectivity. And we will also explore other complementary surface sensitive techniques. I'll just touch upon it, such as neutron reflectivity and GID. In this module, I will talk about grazing incidence X-ray scattering techniques. I will first introduce what is grazing incidence is all about, to analyze the morphology and the structure of interfaces and thin films. These are called indirect techniques because we need to analyze the data to get information such as thickness, roughness, and surface structure. In last modules, we learned about AFM and STM, which are probe-based techniques for direct measurement of the surface morphology. However, these probe-based techniques only look at the top surface morphology. In thin films, we have crucial information on crystalline of the crystalline order, the roughness of buried interfaces that can't be probed with the AFM and STM. In that case, grazing incidence techniques such as grazing incidence, X-ray scattering, GID, X-ray reflectivity, and neutron reflectivity, which can indeed probe the buried layers inside, become very helpful in the analysis of thin films and the structure of interfaces. These techniques are called surface sensitive technique, as X-ray penetrate only a few atomic layers in grazing incidence. I will discuss here X-ray reflectivity mainly, and will also briefly touch upon neutron reflectivity and GID. X-ray reflectivity. Here we see that we have an X-ray impinging on a surface with an angle incident theta, and the refractive index n can be represented as 1 minus delta minus I beta. This is the refractive index for X-rays, where delta is the scattering power and beta represents the observation here. So here you can see that this is a summation which is going over k, which means if you have several kinds of atomic species, one can sum over their atomic numbers and densities and all, and finally get the average delta, which is dependent on lambda, the wavelength of incident light, and electron density, average electron density of the material, and beta is dependent of the absorption coefficient mu, and beta is comparatively very small as compared to delta, almost 2 orders of magnitude smaller. On this slide we see that if we write the real part of the refractive index, which is 1 minus delta, so this is telling us that the refractive index of a medium is less than 1, which is the refractive index which is less than the refractive index of vacuum or air for X-rays. So this is the phenomena. When this happens, what happens? A phenomena of total external reflection takes place. So on the other side you can see that the Snell's law, the equations are written there, and N0 is the refractive index of air, and N1 is a refractive index of medium, and this theta 0 and theta 1 are the respective angles. So when such thing happens, this total external reflection, so this scattered wave is not penetrating into the sample and it makes an angle 0. So we can find out the critical angle which is dependent on the electron density. Just when we see the phenomena in the ordinary light, we all are aware that total internal reflection takes place, and there because the ray is going from denser to rare medium. But here you can see that medium is rather working as a rare medium as compared to the vacuum for X-rays. So the total external reflection takes place in case of instead of total internal reflection here. It is important to talk about here regarding the surface sensitivity of X-rays. X-rays can penetrate several hundreds of microns into the specimen. It has a great penetrating power. It's a high energy radiation. But we know that this X-rays have a phenomena known as total external reflection, just as we have learned it. And due to this factor, we can make this incidence angle of X-rays on the surface less than the critical angle. If it is less than the critical angle, then the X-rays are totally reflected back into the same medium. So here you can see in this figure we have calculated the penetration depth as a function of incident angle into water. The formula for calculating penetration depth is written here as gamma alpha in terms of this alpha, alpha C and beta, and you can see that this penetration depth increases as we increase the incident angle, and at a angle of 0.1 degree the penetration depth is about 70 angstrom. So 70 angstrom is just a 7 nanometer. So this technique is really surface sensitive. If we are probing the surface, then X-rays are penetrating only 7 nanometer into the surface. So we are getting information only from the surface of the specimen. That is why this technique can be made really surface sensitive. In this slide, I'll be talking about the reflectivity of X-rays from a flat surface. Now you can see that this reflectivity is defined as R theta is equal to I theta upon I0, where I theta is a measured intensity as a function of theta, and I0 is an incident intensity. And below this expression, you can see that this reflectivity, this theta can be converted into QZ. This QZ is a wave vector along the vertical direction by using this formula. QZ is equal to 4 pi upon lambda sine theta. And we find that for larger value of QZ, this reflectivity falls as QZ raised to the power 4. And if you see this picture, in this picture QC is represented here arrow. So initially this reflectivity is flat and then it falls down. So this flat region represents the total external reflection. After that, the X-rays begin to penetrate into the sample, and that is how we get the reflectivity of a flat surface. In this slide, I will discuss about the reflectivity from a rough surface. In the last slide, we have seen that the reflectivity from a flat surface. Now you can see in this figure, in this diagram, that a surface is a kind of rough all the time, and this is represented by the equation below, where there is an average surface represented by this line, and this deviation from this average surface is represented in terms of sigma. So the sigma represents the average roughness of the surface, and as we know that even the surface of a pure water or atomically flat surface have a minimum roughness in terms of angstrom or atomic scale roughness. So that roughness is always present in these specimens, but there can also be higher roughness. So finally, we calculate reflectivity for rough surfaces in terms of reflectivity from flat surfaces multiplied by this exponential factor of the roughness. So larger is the roughness, this average roughness, larger, the steeper is the fall in the reflectivity, as we see on this in this diagram, where reflectivity is represented in terms of QZ. In this slide, we go beyond that and we talk about the reflectivity from a flat thin film. Earlier we were talking about reflectivity just from a flat surface from a single medium. But here we have a thin film of different material over a substrate, as you can see in the diagram. So the reflection takes place first at the air film interface and then at the film substrate interface. So this reflection from both the surfaces, when we measure at the detector, it forms an interference pattern, and by calculating the reflectance we can calculate reflectivity just as in this case. So we definitely will have, as this is constructive and destructive interference will form depending upon angle of the measurement, we will observe bright and dark fringes here, which is represented here in the figure, as we see that this is reflectivity profile with oscillations where you have peaks and dips and in periodic fashion. So these dips represent the destructive interference of two X-rays from two interfaces, and this peak represent the constructive interference. And this is a signature. If we get this oscillation, this is a signature that we definitely have a film over a substrate. Usually the film is so thin that we cannot see it from our eyes. It's not observable by even microscope. So when you do this scan and you see that oscillations are there, you become sure that the film is there. And we can estimate the thickness of the film by inverse of this QZ, as you can see in the figure. Before analysis we can just have estimation of thickness from the thickness of the fringes using this formula d is equal to 2 pi upon delta q. Analysis of X-ray reflectivity. So here we go little further, and we here discuss that how the reflectivity of a multilayer or a system with graded electron density can be probed with X-ray reflectivity. So this is a model dependent analysis we do, and we break this entire specimen into smaller layers, and we assume a model at first that these are the estimated electron density of the system. Then we calculate the reflectivity, the total reflectivity using this scheme, and then we compare it with the measured reflectivity which we have measured in the experiment, and then we use the algorithm to fit this data to minimize the difference between this calculated reflectivity profile and measured reflectivity profile. So we have to leave some parameters floating. So when we get this floating, when the fitting is complete, we get this parameters in the end, such as thickness, roughness, and electron density profile. So that way that we analyze the data, so we can really have information about the multilayer systems or systems with electron density graded systems. Okay, so we have now just learned a few aspects of X-ray reflectivity, but let me tell you what are the advantages of these techniques. So it gives information on film thickness, electron density profile along vertical direction, and average roughness of the surface. And it can measure thickness with very high precision of the order of 2 angstrom, let us say. If you change the thickness of the film by that order, it can be detected by X-ray reflectivity. And we can determine the electron density profile of multilayers and roughnesses of buried interfaces from this analysis. And also this is a non-destructive technique, especially for hard condensed matter things, but sometimes if the beam intensity is high, it can be destructive for polymers and organic systems, but we have to be careful. By minimizing the intensity, we can make it non-destructive for organic systems also. Now, okay, so much about the advantages and good thing about X-ray reflectivity. Now let me tell you a few points, what are the disadvantages on this side. So it gives an average information of thickness, roughness, and electron density profile. Just like you saw that in AFM and STM, you could really probe the surface morphology, you could see the roughness and see the local areas. Here we get the average information and not the local information. And if the structure of the film is complex, it becomes sometimes difficult to analyze the data due to non-uniqueness of the fitting. So this fitting procedure is not unique. It gives us a non-unique solutions. So we have to pick up the best solution depending on the information from the other techniques. And large roughness, when the roughness of the surface is very large, say larger than 10 angstrom, then it can really destroy the X-ray reflectivity data, and the analysis can really become very difficult. And the alignment of the sample is very crucial here, because we are dealing with very small angles and very small thickness. So if there is a slight misalignment, we don't observe a good reflectivity, and the analysis that's why suffers. And also a sufficient electron density contrast is required between two media. So when we have, let us say, several multilayers, so if there is not sufficient electron density contrast, the reflectivity will not come out to be good. Now let me just touch upon here the neutron reflectivity. So neutron reflectivity is a complementary technique here. So in neutron reflectivity, neutron beam is used in place of X-ray beam. Rest of the formalism remains the same as we discussed before. So question is, why to use neutron reflectivity at all? In some cases, the poor electron density contrast between two layers of hydrocarbons or organic samples make it difficult for X-rays to distinguish the interface. But we have an option in neutron reflectivity to enhance the scattering contrast by chemically replacing the hydrogen with the deuterium in one system, and for neutron, then hydrogen and deuterium provide a sufficiently good contrast, and we can get really a good reflectivity. In this slide, we have shown the geometrical setup for grazing incidence X-ray diffraction. So first let us talk about the usual X-ray diffraction we work in our laboratory. Usually we make theta to theta scan, and we keep the system in a specular geometry and scan this sample and theta to obtain the diffraction as incident versus incident intensity versus 2 theta. Here GID setup, because we want to measure the structure, or we want to analyze the structure of a film only on the surface, only a few nanometers below the surface. So first we have to make it surface sensitive by choosing a low incident angle, as we have learned that when you have a low incident angle smaller than critical angle, then this total external reflection takes place. And as you can see in this diagram, that we keep this angle of incidence fixed, and the sample can be rotated along this Z axis, and also this detector arm, which you can see that it can be rotated in plane and out of plane, so that we have information of crystalline system in the plane and in the vertical plane. Though in the vertical plane there is not much thickness, but still there can be few layers which can give us the repeated pattern. And you can see here on the other side this two-dimensional layer, which looks like a Langmuir-Blodgett system, where you have a hydrophilic head into the water or on the substrate, and the hydrophobic tail going up. So this you have an incident beam and specular beam. So in a specular beam you observe in the same line of incident beam, just like you do in normal X-ray XRD. But the other arrow, which is shown as diffracted beam, this shows the in-plane variation of this angle in the plane. And by rotating the detector or the sample, we can satisfy this Bragg condition 2D sin theta and lambda several times, and we can really map the structure of a surface or thin films. And important thing to note here is that it is not only the solid surfaces, but we can directly perform this experiment, this measurements on liquid surfaces also. So on this slide we discuss the basic requirement of GID. this high intensity of X-ray source is required first of all. So therefore we cannot do it in using this normal seal tube sources. We need high intense sources. Nowadays it is possible to generate these high intensity sources in laboratory also, but usually this GID is very popular at synchrotron sources. So synchrotron sources are basically sources with very high intensity sources. They have a strong brilliance, a strong larger coherence, and can have polarized beam and pulsed radiation. So here I just would like to just briefly tell the audience that the students that there are a very large number of synchrotrons now around the world if you look, but the prominent ones around the world are this advanced photon source in Argonne, USA, European Synchrotron Radiation Facility in Grenoble, France, and Springate in Japan. And in India we have Indus 1 and Indus 2 beamline and RRCat in India. So these are the strong X-ray sources, and we can use these sources to do surface science, surface analysis, and nanoscience and nanotechnology oriented work can be performed. So students, let's summarize what we have learned in this module. When X-ray falls on a surface with incident angle smaller than critical angle, then total external reflection occurs, which make it a surface sensitive technique. And we also learned that reflectivity of flat surface falls as fourth power of wave vector transfer, and for rough surface it falls even faster. The larger the roughness, the steeper the fall, we can say. And the thickness and electron density profile of the film deposited on a surface can be analyzed using model dependent algorithms, and the accuracy with which the thickness can be determined is very good. And we remember that here we are getting the average information of the surface, and if the surface roughnesses or interfacial roughnesses are very high, then it can really destroy the reflectivity pattern, and we do not see any oscillations which we used to see. So these are the techniques which can be used to study the film thickness. The maximum thickness we can use possibly with the technique is some 1000 of angstrom, maybe 2000 angstrom. If the thickness is larger than that, it's going beyond 1000 angstrom or 2000 angstrom. Maybe if I speak in terms of nanometer, let us say 200 nanometer is the upper limit. So here with these techniques we are talking about only the films which are less than 100 nanometers and their roughness, and we can even analyze the atomic scale roughness. So these techniques are very sensitive, and the complementary technique neutron reflectivity works in same way with a better contrast that can be generated in organic samples. GID finds a structure of 2D monolayer which cannot be identified from usual XRD machines.